Okay, hello everyone. Let's talk about the general steps of finite element method. Here we use FEM as a short. So the general steps of FEM actually um, includes include 8 steps over here. So this is what we usually do uh, with hand calculations as well as using computer softwares. So anytime, either way, we'd better follow the general steps over here to make sure we get a correct results from our finite element model, as well as to avoid any warnings or errors when you create finite element model in Abacus or other finite element softwares here. So now let's talk about the general steps here. So the first step uh, is that uh, step one, we typically discretize the geometry, and uh, select element types. Such as uh, if you have a problem, such as if you would like to find out the deflection of a plate under vertical load, so first step you need to uh, discretize the plate, whether it's a rectangular shape or a circular shape. You need to use some strategy to divide the geometry into smaller uh, regions or smaller um, shapes, such as in rectangular, quadrilateral, or triangular smaller shapes there. So that in the smaller shapes, we can use the approximation of any method to find the relationship between forces and the displacement here. So based on that, we can select the element types. Right? So either you would like to use a plate bending element, or use a solid element or 3D stress element to simulate uh, the deflection under the load, and that's the, the task you need to do in the first step. So the second step, we based on that, we can select the displacement function, the function. Uh, So as we talk about finite element method, please keep in mind that finite element method is a approximation method to solve differential equations. So when we talk about approximation, and the major approximation here is the pre-select uh, selected displacement function, such as you may use a linear function or quadratic function or cubic function to approximate the distribution of the displacement within a smaller region. So that's what you do in the second step. So the third step we call the define element relations. Excuse me. Yeah, after we select the displacement functions, we should be able to uh, find the relationship between stress and strain, as well as the relationship between force and stresses, as well as the displacement and strains. Right? So this is the third step. And the fourth step is derive the element stiffness matrix and the equations. Yeah. So as long as we find out the relations between different physical um, factors here, we should be able to uh, derive the stiffness matrix to represent the relations between forces and the displays for a individual element here. So this is the first step, and the fifth step, we assemble element, element the equations to obtain global stiffness matrix. So after we have the elemental stiffness matrix, we should be able to follow the, the principle of equilibrium, of follow um, the relations between uh, different or adjacent elements to obtain the global stiffness matrix. After that, we will have a system of simultaneous equations. Right? So we can solve for, excuse me, solve for the unknown degrees of freedom, such as if displacement is unknown, we should be able to solve equation to find mm, to find out the values of the unknown displacements or unknown forces. So, and you, because typically globally, for any given problem, you will know the global forces and the global displacements here, global boundary conditions here, so that you can use those known variables to solve for the unknown variables in the step 6. So after any global uh, displacements or forces are solved, we should be able to go back to the element. So we should be able to solve for the element stresses and strain, strains. So if everything, yeah, so that's the step 7. After that, we can interpret the results. Yeah. So this is the general steps for any finite element models. So if you use hand calculations, basically you need to follow all the 8 steps one by one. And if you use computer software, so actually, after you do the step 1, you discrete the geometry and select the element types, and software will do the remaining from step 2 to step 7. So the only thing you need to do is to interpret the results. And so steps 2 through 7 is pretty like a black box of the software. So um, you the only thing you need to do is to input some number and get some number from the step 8. But it is quite important that um, you develop some knowledge in the theories as well as the typical procedure of how the software works here. So I think that's very important for you to get a reliable or accurate finite element analysis results using any software. So basically, for this semester, we will focus the first half of this semester. We will focus on the procedure and the series of this finite method over here, to make sure you develop some understanding and knowledge in the fundamentals and the principles here. So the second step semester we will focus. Second half um, will be focused on mm, um, the the practice or exercise of using abacus to make sure you can handle problems with complex geometry as well as complex loading conditions. So this is the plan for this uh, semester over here regarding the procedural finite element method over here. So now I'm going to give you a quick example to see how we can solve typical problem using finite element method. So we have an example here. So this example is very straightforward. So if we have we are required to determine the nodal displacements, the forces in each element, and the reactions using the Feynman method. So I believe all of you can solve this problem by using the method you learned from mechanics of materials. Right? So we have 10 kilonewton here, and so we have so 3 nodes here. So 1 and 2, 3. So basically we have 2 bars here, and um, one bar actually, 1 bar here. Right? So the bar is discretized to 2 elements. So we have it, and so that we have 3 nodes here. So we know that the length of each element is 1 millimeter, the 1 millimeter, and then we have the modulus of elasticity given here, and then we have the area here. So I believe everybody can quickly solve the reaction force at load 1 here. So if you are given a 10 kilonewton at node 3, the reaction force at node 1 should be 10 kilonewton, and the forces in element 1 and 2 is pretty much um, is the same as the 10 kilonewton here. But here we will not use the method we learned from statics or mechanics materials, where we use a different procedure as shown above. Right? So using finite method here. And now let me show you how we can use this procedure here to solve for this problem. So solutions here. So if you are using finite method, that's step 1. We just write the displacement matrix. Different. So the question here is how many displacements we need to consider here. So we have 1, 2, 3 of those in the two-dimensional space. So theoretically, we need to consider the movements of 1, 2, and 3 in horizontal and vertical directions. Right? So that means theoretically, we need to consider 2 displacements at each individual node here. But for this case, since the force is collinear with the bar, there will be no movement in the vertical directions, right? So that we can automatically eliminate the displacements in the vertical direction, so that can reduce the size of the problem here. So here that means we only need to consider. So if we write down that displacement matrix, we only need to consider the movements in the horizontal direction. Right? So we use the U1 for horizontal movement of node 1, U2, U3. So those are the displacements we need to consider over here. And based on that problem statement, we should be able to tell which one is known and which one is unknown too, correct? So we should be able to get, so the U1 is fixed, so that's 0. U2 and U3 is unknown to us. This is the displacement. Quite easy. Right? Yeah. Step 2, we write down the force matrix. Yeah. And so we have all the forces here. Yeah. So we consider the force in node 1 in the x direction. Okay. So that's in the horizontal. So x is the horizontal direction. The horizontal direction. So fx similarly f2x and f3x. Please be aware of the subscript for the forces. Right? The first symbol means that the force at the load where the force is applied. The second one is the direction of the force. So all the forces are in the x direction. We do not consider the force in the vertical direction because we know that the force in the vertical direction will be 0. So yeah. So here we can also tell which one is known and which one is unknown. So for F1x, because there is a reaction force, so that's F1x is unknown to us. F2x, is there any? Since there is no force, no external force applied to node 2, so that we put a 0 here. Similarly, for node 3, we have the minus 10 kilonewton here. That's a force matrix here. So as you can see here, by using finite method, this you should be able to write down the displacement matrix and the force matrix very easily. Similarly, computer does this very quickly. And we just need to input a list of numbers here, so that the computer can tell which one is known and which one is unknown. So the next step, we write down the stiffness matrix. So step 3, and rewrite the stiffness matrix. So the general stiffness and the global stiffness matrix. And since we have three displacements and three forces, and so the relation between the forces and the displacement will be a matrix of 3 by 3. So we have the K11, K12, K13, K21, K22, K23, K31, K32, K33. So this is the stiffness matrix here. And so this tells us that. So that means that here, up to here, we need to figure out the values of the elements in the stiffness matrix. So there are line or low numbers here, and we need to figure out them. So by doing a structural analysis, we should be able to tell that. So because based on structural analysis, we know that the K11 represents the force where you fix the other degrees of freedom and you apply a unit for displacement that the force you need to induce a unit displacement here. So that's a force. And if you fix the others, so in this case, we should be able to derive the value for U11, right? U11. So here we have the system here. System here, and we have the load 1, 2, and 3. We have the load 1, 2, and 3. The K11 represents the force that is required to induce a unit force, a unit displacement at node 1 when the other degrees of freedom are fixed. So now firstly we fix the other degrees of freedom over here. So then when we induce a unit displacement, we induce a unit displacement here. So that means that we have a unit if we have a force in K11 here, so the K11 will induce a unit displacement at node 1 into the positive direction. So based on mechanics materials, I think you should be able to tell the magnitude of the K11, right? So the K11 should be equal to the K11 should be equal to the EA over the length times the displacement times the displacement. So that's equal to, we have already get the number 210 gigapascal times the area. That's 4 times 10 minus 4 meters square over the length. And so the length is 1 meter here times 1, so that we can get. So it's yeah, we have the gigapascal times meters. So we just get the so this is a force that is needed to induce a unit displacement along the one when the other fixed and the other fixed. So this is a K11 means K11 means. Yeah. Does this make sense? Yeah. Okay. So similarly, the K12 should be the force when in the the reaction force at node 2. So K1, 2, and if we have the K1, 2 here, we use a different color here. Maybe just, so the K1, 2 here, this is a K1, 2, this is a K1, 3, K1, 3. And so in this case, the K1, 2, K1, 2. And if we take, we assume the K1, 2 is in the same direction of the positive direction, so the K1, 2. But we know the K1, 2 will be a negative value, right? So the K1, 2 would be equal to K1, 1 in this case. The K1, 3 will be 0 because 2 and 3 are fixed, right? So K1, 3 would be 0, would be 0. So this is K1, 1 and K1, 2. Okay. So similarly, we should be able to get the K21 and the K22, and we using the same procedure, similarly. Yeah, similarly, and if we have the 1, 2, 3, we fix the 1 and 3, and we induce a unit displacement for node 2. So the force, I'm just going to use blue. The force at node 2 is K22. So the reaction at this is K23. And here, this is K13. K13. So it's pretty straightforward here. So the K, K1, 2, sorry, K2, K21, sorry, should be K21 here. So in this case, the K21 should be equal to the minus EA over L. So that's equal to minus. And K22 is equal to 2 times EA over L. And the K23 is equal to minus EA over L. Very straightforward, based on the definition of the stiffness coefficient in a structure system up here. Right? So similarly, we can get the values for the elements in the stiffness matrix of the third row here. So here we have the K31, that's equal to 0. K32, that's equal to minus the K33, that's equal to, so that we can have the K. So we go step 4. Go to step 4. You have the K times D equal to the force, so that we can have, we just get write down all the numbers of the stiffness matrix. Times 5 meter times the displacement. So we have the displacement that we use equal to F1 x 0 and then minus 10 kilonewton. So this is the relations on the relation between displacements and the forces here. So actually, there are three linear equations here, three unknown variables. We should be able to solve for all of them. So solve for U2, U3, and F1x. That should be easy. So because we have the 0, so we can just neglect we use the second and the third equation to find the U2 and U3. So we have the times U2 and U3 is equal to 0 and 10 kilonewton. Because we have the 0 displacement, so that we can neglect we can use the second and the third equation to solve for U2 and U3 here. So then we have the U2 and U3, two equations, two unknown variables. So U2, that's equal to minus millimeters. That's equal to minus U3 millimeters. That makes sense. So under a compression, both U2 and U3 will be in the negative x directions. So if U2 and U3 are known to us, so then F1x can be solved. Equal to K12 times U2, and that's equal to times minus 0.119 millimeters. So that's equal to 9.996 kilonewton. That's so the reaction force in node 1 will be 10 kilonewton, which is consistent with the value which we can obtain from the mechanics of materials method here. Right? So yeah, a little bit calculation error over here because of the solution of the linear equations here. So 9.996, but the error is very small, very small. So yeah, so I think that's how we solve for displacement and forces using finite method for a very simple structure that you should be able to use the approach where you learn from mechanics materials. But here we will use finite method for this type of problem through this entire semester. I think that's all for the general steps of finite method here for today. Thank you.